Okay, welcome back. In this section, we're going to look at our second derivative test. Our second derivative test examines the concavity of the graph. The concavity of the graph is, I like to describe concavity as just whether if it's concave up or concave down, is basically will the graph hold water, will it not hold water. So something that's concave upward would be like a parabola like this. Like that would be concave up over its entire interval. And if the water will spill out, then it's concave down, something like that. If the graph were to be like some sort of a polynomial or some sort of graph that does like this, where it has different changes in concavity, that point where the concavity changes, let's say that point right there, that's going to be called a point of inflection. We're going to take a look at all of those things. In our second derivative test is kind of similar to first derivative test. If the second derivative of a function on the interval is greater than 0, then we call the graph concave up. If the second derivative is less than 0, then we call the graph concave down. Sometimes there will not be a change in concavity at a potential point, so we have to kind of look at that. Also on the second derivative test, we can identify points of inflection. We say that the point C f of x is going to be a point of inflection if this is true. These things are true. First of all, if it's got to be continuous at C, and then there's a point at C in which the concavity changes, where it goes concave up to concave down. So what you're going to do is, the process here is you're going to take the second derivative, you're going to find the second derivative, you're going to set it equal to 0, you're going to solve it. Those are possible points of inflection. Set up your number line. Once you set up your number line, you're going to determine whether the second derivative is going to be positive or negative. If it's positive, it's concave up. If it's negative, it's concave down. Simple as that. If you have a change in concavity, then it's a point of inflection. If you don't have a change in concavity, then there's no point of inflection. Second derivative test also can help us find the extrema of the function. What this is saying is that if the second derivative is less than 0, in other words, the graph is concave down at a critical number, okay? The graph is concave down at a critical number. That's a concave down graph. Here's my critical number right here. Then that critical number must be a max. If the graph is concave up at a critical number, say like right here, that's concave up at a critical number, then that must be a min at that critical number. So we're going to put that all together with our example here. I just have one example for you. Again, finding the derivatives can be some of the most difficult parts of this. You need to find the first derivative. So f prime of x is going to be 4x minus 4x cubed. Set that equal to 0 to find your critical numbers. Factor out the x, or factor out the 4x, times 1 minus x squared equals 0. And you find that you have critical numbers at x equals 0 and then plus or minus 1. We're going to look at what's going on with the concavity of the graph at these values to know whether these are maxes and mins. If I wanted to discuss increasing and decreasing, I'd have to use first derivative test. Find the second derivative, which is 4 minus 12x squared. Set that equal to 0. That equals 0 at x equals plus or minus the square root of 1/3. The AP folks don't care if you simplify that at all, so why simplify it? Go ahead and create your number line chart. Here's the negative square root of 1/3. Here's the positive square root of 1/3. Now we're going to look at the second derivative. We plug our test values in the second derivative. So on this first interval from negative infinity over to negative square root of 1/3, let's use -1. If I put -1 in here, I get 4 minus 12, which is negative. On this interval, let's use 0. If I put 0 in here, it's positive. And if I put something beyond 1/3, square root of 1/3 in here, say 1, I get negative again. What those positives and negatives will tell me where the graph is concave up and concave down. So we say the graph is concave down on the interval from negative infinity to negative square root of 1/3. That's not included, union with the square root of positive 1/3 to infinity. That's where the second derivative is going to be negative. The graph is concave up on the interval from negative square root of 1/3 to positive square root of 1/3. And we have points of inflection at x equals plus or minus the square root of 1/3, because the concavity changes there. Now, if I go back to my critical numbers right here, if I go back to these critical numbers, 0 falls in this interval, -1's over here, and +1's over here. Since the graph is concave down at -1 and +1, then those have to be maximum points. So up here, f of plus or minus 1 are local maxes. And since the graph is concave up at 0, f of 0 is a local min. If by chance the first and second derivative were 0 at a critical number, then you don't have enough information. You have to do some more exploring to know whether that's a max or a min. Again, finding your derivatives, set them equal to 0, and solving it, some of your hardest stuff. Once you have that, then applying these theorems are not too bad. Applying the first derivative test or second derivative test, we can put it all together. These local maxes and local mins you can determine from first derivative tests. You do not have to use second derivative test ever. I will never tell you you have to use second derivative test. The AP folks will never tell you that. The only time you must use second derivative test is to determine concavity of the graph and the points of inflection. All right, best of luck.